One day, a friends group gathered to discuss their issues they were facing in their business. One was facing issue how to earn maximum profit from his business. The other person issue was how to minimize the cost of the desired diet. Third person was discussing about the transportation of the product to different destinations at a minimum cost. Actually, their issue was based on different types of linear programming problems. And let me explain to you one by one. The first type of linear programming problem that we have here is the manufacturing problems. And the second type we have is the diet problems. And the third type that we have is the transportation problems. So we have manufacturing problems, diet problems, and transportation problems. First, we will discuss about the manufacturing problems. What is manufacturing problems? Manufacturing problems deals with the number of units of different products produced and sold by a firm when each manufactured product requires fixed manpower, machine hours, labor hours, etc. to make the optimum profit. Let's see one example. One kind of pancake requires 200 grams of flour and 25 grams of fat. And another type of pancake requires 100 grams of flour and 50 grams of fat. Find the maximum number of pancakes that should be cooked from 5 kg of flour and 1 kg of fat, assuming that no shortage of other ingredients used in making the pancakes. And formulate the above as a linear programming problem, and you have to solve this graphically. So there is a lot here, right? You have some quantities in flour, then you have in fat, and then you have the total amount that is less than, it should be less than 5,000, something like that. So when you look at all this, you can see that you have to formulate a linear programming problem. So you can see there are pancakes. So I take X pancakes as type 1 and Y pancakes as type 2. And my LPP or my linear programming problem here is to maximize Z, that is X plus Y. So I need to have the maximum number of pancakes so that I have certain constraints also. So their constraints are different. So let's stick to the maximizing thing over here. That is, I need the maximum number of pancakes, that is Z is equal to X plus Y. Subject to the constraints. What are the constraints? The constraints are X greater than or equal to 0, Y greater than or equal to 0. Both X and Y should be greater than or equal to 0. Basic constraint. The second constraint, 200X plus 100Y less than or equal to 5,000. That is, the total amount of flour used should be less than or equal to 5,000. This is the first constraint. And the second constraint, or before going to the second constraint, you can see that this 200x plus 100y less than or equal to 5,000 can be minimized and written as 2x plus y less than or equal to 50, the first constraint. And when you get the first constraint, that is not over. You have to draw a graph for that. So when you draw the graph for 2x plus y less than 50, I'm drawing here for equal to 50, but when you draw for less than 50, that 2x plus y is equal to 50, and then the area below, or the area this side of 2x plus y is equal to 50 should be shaded. And this is not over or final. You have other constraints also, right? And we have the third constraint, that is the total, that is 25x plus 50y should be less than or equal to 1000. Or from this, I get x plus 2y less than or equal to 40. So this is the third constraint. On plotting the equations, we notice that shaded portion is the optimum solution. So you can see that I have 2x plus y is equal to 50 and x plus 2y is equal to 40. And I have shaded the area common to both here, the gray area. So I got the area, and from that area, I am getting the points. That is, from that, I get A, that is 25, 0, B, that is 20, 10, and C, which is 0, 20. Using that, we have to get the tabular value, that is Z is equal to x plus y. And what are the values? When you put A 25, 0, I get 25 plus 0, 25. B 20, 10, I get 20 plus 10, that is 30. And C 0, 20, I get 0 plus 20, that is 20. So you can see that the maximum value or the maximum number of pancakes within the constraints is given by what? The one over here, that is the maximum value is 30, and that is when x is equal to 20 and y is equal to 10. That means 20 pancakes of type 1 and 10 pancakes of type 2 should be there to maximize the total number of pancakes, that is according to the constraints also which is given in the question. So what we have done here is we looked at the question, we formulated an LPP or a linear programming problem, then we have drawn the graph and we shaded the common area for that particular graph, and we got the final maximized number of pancakes that we have to make so that there will be a profit or there will be the following constraints which are followed. So now let's look at the next type of problem, that is the diet problem. So whenever we are having diet problems, it deals with mostly determining the number of different kinds of constituencies or nutrients in your entire diet, or sometimes to minimize the cost of the desired diet, and sometimes it contains a specific minimum amount of each constituent or the nutrient inside that. So these will be the different cases when you do questions which are of what? Diet based questions. Now let me give you an example to make you understand more clearly. A diet contains a minimum of 80 units of vitamin A and 100 units of minerals. Two foods F1 and F2 are available. Food F1 cost is rupees 4 per unit and F2 cost rupees 6 per unit. 1 unit of food F1 contains 3 units of vitamin A and 4 units of minerals. 1 unit of food F2 contains 6 units of vitamin A and 3 units of minerals. Formulate this as an LPP or a linear programming problem and graphically find the minimum cost of diet when the mixture of these two foods is taken and it meets the minimum nutritional requirement. So that is a question. Now to find the solution, let X units of food F1 and Y units of food F2 be mixed. And the LPP is to minimize Z, which is 4x plus 6y, which is subject to the constraints x greater than or equal to 0, y greater than or equal to 0, and 3x plus 6y greater than or equal to 80. Now, for the graph for the corresponding function, that is 3x plus 6y is equal to 80 or greater than or equal to 80, will be an upper graph. And for the next case, that is, or the next constraint, we have 4x plus 3y greater than or equal to 100. And this graph, if I plot, I will be getting another area which is 4x plus 3y greater than or equal to 100. That is on the other upper side again. Now, if I see the graphs, I have two lines and two areas which are shaded, right? And what is the common area to both these graphs? This purple colored area will be the common, that is the shaded area for this particular LPP. And from this, we understand that the shaded portion gives us the optimum solution for a particular LPP, that is a linear programming problem. So now, if I have the points and to minimize Z is equal to 4x plus 6y, now the first point, that is A, in the common area, we have a point A which is 80 by 3 comma 0, as you can see in the graph. Just go to the previous slide and you can see that A 80 by 3 comma 0 will be a common point. And what is the value there? It will be 320 by 3 plus 0, which is in total the cost will be 106.66. Next point, or the corner point, that is B, which is 24 comma 4 by 3, will give us a value that is 96 plus 8, which is equal to 104. Okay, let it be there. Now C, that is 0 comma 100 by 3, will give the total value as 0 plus 200 or 200. Now from these three values or these three costs, look at the minimum one. The minimum cost will be 104, that is the minimized cost for this particular LPP. So that is what we get here from this graph. Now, what is a feasible region? It is an unbounded region because it is going many places. Like you can see that graph extends towards infinity. The solution region 4x plus 6y less than 104 or 2x plus 3y is less than 52. No point lies in the feasible region. There is no point because this graph is extending infinitely, right? So the cost is minimum at what point? The point B, which is 24 comma 4 by 3. And what is the minimum cost? It will be by calculating, that is x is equal to, putting x is equal to 24 and y is equal to 4 by 3. You will be getting that as 104. That is the minimum cost. So that is how you find the minimum cost. Now look again in the graph, you have all the points over here. So you have the point B 24, 4 by 3, and you have a dotted line which is passing through that particular point B, which is 24 comma 4 by 3. So that is how you get the minimized cost here in this particular LPP. So hence 24 units of food F1 and 4 by 3 units of food F2 must be mixed together to get a minimum cost of rupees how much? 104. Now let's start with the third type of problem, which is a transportation problem. Transportation problems deals with determining a transportation schedule to find the most affordable way of transporting a product from plants or factories situated at different zones to different markets. Let me exemplify which will help you in better understanding. If a man drives his motorcycle at 25 km per hour, he expends rupees 2 per kilometer on petrol. If he drives at a faster speed of 40 km per hour, the petrol cost increases to rupees 5 per kilometer. He has rupees 100 to expend on petrol. Now, what will be the maximum distance he could travel in 1 hour? So that is a question, or that is a case here. So listen to the case again, and what will be the solution? So let the person travels x kilometer at 25 km per hour and y kilometers at 40 km per hour. And the solution for the LPP, that is, you have to maximize z, that is x plus y. So what is the total distance? That is x plus y, which is subject to the constraints x greater than or equal to 0, y greater than or equal to 0. And what is the second condition? Very important condition, x by 25 plus y by 40 less than or equal to 1. So that is how you get the first constraint, or from that first given transportation problem. And now when you draw the graph for x by 25 plus y by 40 is equal to 1, I get a graph like this, right? So that graph, I have a shaded region over here, that is a green region. Now, there is another condition, that is 2x plus 5y less than or equal to 100. So that is the next condition. So when there is a condition like that, you can see this line, that is the blue line over here, that is 2x plus 5y equal to 100. And for less than 100, it will be a region which will be shaded in this downward direction. Now, looking at both the graphs over here, the green one as well as this blue one, I can see there is an area common to both these, right? And what is the area common to both this? This gray patch over here, that is the area which is common to both. And when you see that area, I have some corner points. I have one over here, C, another A, and another B. So I have 3 different corner points here. What are the values of that points? A is 25, 0, B is 50 by 3, 40 by 3, and C is 0, 20. Now, to find the total solution, you just look at the shaded portion and you get the feasible solution, right? And when you look at the points, you take the first point, that is A, 25, 0, and put here, you get 25 plus 0, that is a value 25. 50 by 3, 40 by 3, you put it here, you get it as 30. And C, when you put, you get 0, 20, or the 0 plus 20, that value is 20 itself. Now look here, what is the maximum value? When do you get the maximum value? When you put it at point B. And what is the maximum? It is 30. So that is how you get the answer for this particular LPP, right? So you have to maximize the total distance. And what is the total distance it can travel? Depending upon all the constraints, it is 30 km based on these different conditions. So hence, he must travel 50 by 3 km at a speed of 25 km per hour and 40 by 3 km at a speed of 40 km per hour for a maximum distance of how much? 30 km. So that is how he can maximize his total distance here. Will we be able to solve allocation problem using the above discussed methods? That is, using LPP, can we solve allocation problems also? Do check for all these things. And before that, let's have a quick recap of what all we have learned.
Manorama Horizon, learning made simple.